Good afternoon. Let's start the colloquium. It's 4 past. I think we can start. So it's a pleasure to have here today Lehner from Parametric Institute from Canada. As you know, whenever there is a workshop at ICTP, so we kindly ask one of the person involved in the workshop to give the colloquium. So the workshop on application of gravity just ended, and actually we'll end with this colloquium. So there was the handing of the PhD prize in gravity, and it makes sense that it's Louis to wrap up this activity. So Louis is not a guest here. I mean, he has from Parametric Institute, he has many ties with ICTP, many common activities. And so he's part also of the board of ICTP, so he's really part of this community. So he started his undergraduate studies in Cordoba in Argentina, but he soon moved to the United States for the PhD in Pittsburgh. Then after a series of postdocs in North America, he first landed in Louisiana and then to his present position. Among other things, he's one of the 10 most influential Hispanic Canadian people, so bear this in mind. and of course, he's active in the area of gravity, gravitational waves, all aspects of theoretical and phenomenological gravity. And he's an expert in strong gravity. You might think it's a contradiction, but it's not. Strong gravity is a subject of huge amount of investigation nowadays. And in particular, today, the main focus of his talk, it will be some applications of the recent detection of gravitational waves to the structure of black holes, one of the most fundamental objects in nature that we know. So, Louis, please.
Thank you, and thanks for everyone for coming. Thanks for that introduction. It's always a pleasure to come to Sao Paulo, in particular, ICTP-SAIFR. So I'm from Argentina. Every time I step foot in South America, I feel like I'm home. Okay, so you might wonder, why do I have some striped animals there? There's a point, and I'll try to make it as I go through my talk. So not sure if you heard the story of this legend that Pablo Escobar had a big farm in Colombia, where he had lots of African animals, in particular zebras. But the legend is that at some point, the zebras were not there because they hadn't arrived, and he wanted to impress some of the guests, and so they grabbed donkeys and they painted stripes. These are not those zebras, because that's a legend. These are real donkeys that were painted in a zoo somewhere. I'm not going to say the country, it doesn't matter, but the point is you can do a pretty darn good job making a donkey look like a zebra. And yesterday we had a really nice talk by Raul, who in the second part was talking about machine learning and their ability to discern things given some score. I wonder how well one of these machine learning techniques, what would be the score of thinking that this is a zebra? You don't think it would be good? You think they would tell them apart? Okay. So anyway, so this is part of, you're just going to see as I go through my talk why I bring this up. There is a little bit of a controversy going on, which will gain some steam till we actually resolve it. You might think that it's a lot ado about nothing, but there is a lot riding on this. So hopefully I'll go through this in a clear manner. So I also need to say something, or I start with a caveat for my talk. For the past few years, we have been testing this new way of doing seminars in group meetings at Parametric Institute, where we ask the speaker, come with a punchline. Your talk is only 10 minutes long, and the audience will drive their next hour. So I'm doing a sort of hybrid here. I don't have a lot of slides. Please interrupt me at any moment. I can go on a tangent and talk about anything that is related to what I'm going to be saying, and I will just move around quite a bit. So by all means, please keep this interactive if you can, or if you will. We find this mode of doing seminars quite useful because it actually is very conducive to especially young students asking questions. Typically students tend to be shy because they're afraid of opening their mouth, asking a question, because, oh, maybe I should know about this. Well, but if the speaker is not telling you everything, you have plenty of excuses. You're not supposed to understand everything, so you ask questions. And so in our experience, this has been pretty good at engaging students, especially in the time of COVID. Okay, so what's the setup? So of course, as you know very well, we're in the era of gravitational wave astronomy. It got started in earnest a few years ago, 7 years ago, with the first gravitational wave detection, the first direct gravitational wave detection. And now, kind of all windows are open to ask many questions in many fronts, and I'll talk a little bit about some of them, and then I will home in a very particular point or a very particular topic that, as I said, has become a little bit controversial in the past few months. So, I mean, underlying everything we do in astrophysics, cosmology, even particle physics nowadays, is this famous equation by Einstein, an equation that Ricardo has told his students during his class. So on the left-hand side, we have the Einstein tensor, and on the right-hand side, we have two contributions, one given by the matter content, and the other one given by the cosmological constant. And we know this embarrassing reality that about 75% of the energy and matter in the universe, we don't have a clue what it is. It's dark something, either matter or energy. And okay, we shoved quite a bit in there, like we have 75% in there, or 70-something is in there. And there are 20%, it's dark matter, which maybe is somewhere there. But there are quite a bit of efforts to try and say, well, maybe this is not, it's the left-hand side that would have to be changed. It's not a Riemann tensor, it's something else that is kind of describing gravity in a slightly different way, not as this dictated by Einstein's theory of relativity. And then we're trying to, in more than one way, explore what gives. So the type of kind of test that we have been going the community-wide to try and test general relativity range in many aspects and through many years. But two particularly interesting number or combination of numbers is the following. So in the horizontal axis is essentially the gravitational potential of typical sources, or the gravitational potentials that different experiments are targeting. And here is you say, well, given a source that has some amount of mass m and some characteristic size L, the m over L is telling you how strong the gravitational potential of that object or that region is. And if you move all the way to order 1, this is where black holes sit. The other axis is the curvature axis that basically tells us how strongly curved within this picture of general relativity the space-time is and what is an associated length scale to it. And okay, we go from very small values to, again, order 1. And for going here, order 1 in both directions, we're talking about black holes that are quite small. So gravitational wave detections targeted by Earth-based detectors so far are kind of probing this region. The Event Horizon Telescope, which is probing the vicinity of a supermassive black hole, covers through this region. So even though it's reaching potentials that are of order 1, of course, every time you talk of a black hole, you're sitting somewhere here. But because it's targeting supermassive black holes, the scale is much smaller. And of course, then we have done quite a bit, or the community has done quite a bit through pulsar timing and pulsar measurements. And this goes quite a bit there, doesn't quite go all the way up as gravitational waves, but for a number of sources, it's quite competitive to what gravitational wave detectors on Earth-based detectors we can get. And with that, a significant number of constraints on potential deviations from gravity has been put forward. But of course, the most exciting regime is right here, when you try and push in the most extreme regime. And this is part of what I'm going to be trying to talk today and related to that controversy. Just to put things a little bit in perspective about what's happening and what's coming. So far, we have detected gravitational waves directly through ground-based interferometers. And these are targeting black holes or neutron stars, objects that have between, say, a few solar masses to 100 solar masses. This is the range in frequencies that you can reach. Space-based interferometers, of which LISA is the better known, but there is a Chinese one that is also kind of gathering quite a bit of steam, and hopefully they will be up sometime in the future. So this is targeting the end of the 2030s detectors. They are targeting smaller, lower frequencies because the frequencies of gravitational wave decay or goes inversely with the total mass of the system. And so their main targets are supermassive binary black hole mergers in particular. If we keep going down in frequencies, what we can do with pulsar timing arrays, so the idea is you detect the pulses coming from a collection of pulsars, and if there is any delay or change in the period between pulses, maybe a gravitational wave went through, and this set of collaborations, there are actually 3, maybe 4, are collaborating nowadays, and there is all the expectation that sometime in the near future, maybe next year, they will come out with some announcement, perhaps constraining the potential background of gravitational waves of supermassive binary black holes that are far from colliding, but are producing gravitational waves nevertheless, and their collective signal would hopefully provide a background to these detectors. And if that signal is not there, well, maybe there is further indications of this last parsec problem, which is this very famous problem in astrophysics, where if you imagine 2 galaxies coming together, each galaxy having a black hole, it's hard from theoretical considerations to find out how these 2 black holes will come together in a time that is less than the Hubble time, unless you invoke some very interesting mechanisms to accelerate the merger history when they are pretty far apart. And another, this is not direct detection of gravitational waves, but it's indirect, which comes from primordial gravitational waves that get themselves imprinted in the CMB. There was a claim some years ago that then was retracted, but detections are getting sufficiently accurate that hopefully we'll get to hear something in the next few years about that. So just one slide on this, and if you want more details, please ask, or you can, I also strongly suggest you take a look at our Kisman talk earlier today, which was beautifully explaining some of the techniques that gravitational wave detection use today and what's involved. But typically, there are some exceptions. Typically, what gravitational wave detectors do today is they're trying to get gravitational waves that are very buried in the detector's noise. So a typical detection of in LIGO, Virgo, and Kagra these days is kind of like this. You have noise, and very deeply hidden in it, a gravitational wave is to be found if you do the right job. So what's the task to do that? Well, you need a set of templates, something to help you go search in the haystack for that needle. You create gravitational waves for all possible things you can imagine might exist, and then you go through the noise, and then you do this so-called match filtering. So you go one template after another through every single chunk of data that you have, and if there is a coincidence, then you dig the signal out of the noise, and that best match not only tells you just detected gravitational waves, but more importantly, is telling you what the parameters of the source are, and with that, you start doing astrophysics. So in particular, you extract the masses of the systems that are coming together, their spin, and their distance. So all that intrinsically is a major piece of information for astrophysics. So one of the greatest promises of gravitational wave detection was, I always teach my particle physicist friend that, well, you're going after the Higgs back before they detected. But if you get it, only 50% of the chance will be an exciting result, because you either find it where you thought it should be, and so what did you learn? Nothing. Or it was somewhere else, in which case it's pointing to new physics, and that would be exciting. For gravitational waves, we had the luxury of either way, it's great. If it misses general relativity, you have something new to do. If it's exactly as expected in general relativity, you're doing astrophysics, which again is something new, and we are seeing both playing out nowadays. Eventually, the better detectors are coming online. The ones I mentioned on space would have a signal to noise, or a noise level, if you want, much reduced when compared to the gravitational wave signal. And there are third-generation detectors that will come in the 2040s, where in reality the signal will be much louder when seen in those detectors, and the noise will introduce a jiggle, which of course will not prevent you from seeing the waveform, but you still will need to do this match filtering to get a good information of what the best match to the signal is so that you can do physics. Of course, the techniques is expensive. You need to create the templates. There's major work on the theoretical front to create those templates. And for instance, Ricardo leads one front in trying to understand the early part of the signal. I'll say a few more things about it in a second. But once you have the templates, you need to encode that information in an efficient way so that it can go and then perform the analysis. You might have gazillion templates that then you have to go and beat against the noise every single time to try and find which one is the one that has the best match. And once you have all that, well, on the gravitational wave plate, you can do astrophysics, you can do particle physics, you can do cosmology, you can do fundamental gravity. My talk is going to be mainly covering this point, or one particular question along this line. But here, there's already plenty of very interesting features that have been understood. And just to mention a few examples, for instance, in the context of astrophysics, by now, gravitational wave detectors have measured about 100 binary black hole mergers. Those binary black hole mergers have informed the population. We went from not having direct evidence of any black hole out there to having now 100. We now have the distribution of their masses, both in the mass parameter, but also in the distance. And it's already kind of giving some hints of some interesting features. For instance, some of the black holes that are the most massive that have been found are already pushing on theoretical ideas from astrophysics front that thought there was a very hard limit to the most massive black hole you could form, which was about 55 solar masses, before something will prevent that black holes between 55 and above 100 to form. Now you go with gravitational waves, you have something that is 65, it's already pushing on these astrophysical models. There were also, this was called the upper mass, or it's called the upper mass gap. In the distribution, there seemed to be also an overabundance around some masses of black holes. Still, this has to be firmed out. But if that's true, it's hinting of a possible different channel of formation, and maybe some of those are black holes of primordial origin, which will have something to say about the dark matter models in the universe, for our universe. There is also pushing back on something called the low mass gap. It was believed, primarily driven by observations, that there shouldn't be black holes with masses lower than 5 solar masses. Yet LIGO has already observed objects of 2.6, 2.9, or thereabouts. So either you're finding the most massive neutron stars in the universe or the lightest black holes from astrophysical origin. And again, this is giving a lot of food for thought for astrophysics. In particle physics, there are very interesting models, say, to explain dark matter, one of them being the axions. And axions are some massive fields that, when interacting with a black hole, can lower the spin of a black hole in a significant manner. So by scanning the possible set of angular momentum that black holes are observing, you can put constraints on that particular dark matter model. In cosmology, we're seeing the very early efforts that using, and this is something that Kishman also discussed in his talk very beautifully, provide an independent way of measuring the Hubble constant. Of course, it's still not competitive because the errors or the potential width of values is still too broad to be fundamental in cosmology, but it's something that will only get better as more signals are detected. So that was just a little bit of a hint or a glimpse of some of the activities that are going on. But for the purpose of my talk, I'll be thinking mainly on, well, how can we then use this information to detect test general relativity and some of the problems that we have to face in there. So as I said, well, with gravitational waves today, we're extracting physical parameters, understanding the sources. We are struggling and working hard at encoding very efficiently the gravitational waves, but typically, let's say gravitational waves are looking like this. So there's an Erlang spiral where these objects are going around each other. The good description for them is can be obtained with post-Newtonian expansions, or expansions that rely on the fact that the velocities are low and the orbital frequency is low, and you can rewrite these equations in a way that mimics Newtonian relativity with several correcting terms, and it's harder and harder to compute further corrections, and this is one of the things that Ricardo does, but you're actually getting a better and better description of the early part. At the late part, you assume, and there's something that was called the ultimate state conjecture. That is, it's a conjecture, I'll say a few more things later, that says that the ultimate object that you form when there is a collapse in the universe is a black hole. And that black hole is described by something called the Kerr solution, and we'll get more into that in a second. But that gives you a recipe to obtain a pretty reasonable description, and how reasonable is the key of this talk, for the after merger. And in between, you have to use numerical simulations, put everything together, and encode that information. But what does it really mean to test generativity? Well, at the very basic level, you can do a null test of GR. So if you know everything that you should expect in generativity, you go to your signal, you test, and you say, is it sufficiently consistent with it that I can discard a hypothesis that it's not generativity? So the outcome is two. Either you're consistent with generativity to within some tolerance, or you're not. So far, every single test says you are consistent with generativity. But if the test were to say it's not, even that null test that will say, no, it's not described by generativity, doesn't tell you yet what is the thing that is replacing it. So for that, you need better tests. So there are tests that are called parameterized tests, where you go to your signal, and short of knowing what a putative best alternative solution should be, you modify ever so slightly the parameters away from the ones preferred by generativity, and you ask the question, is there a preference for this value to be off from the value from generativity? This is what the LIGO scientific collaboration is doing nowadays very, very deeply. There are others that say, well, just take the best match from generativity, you subtract it from the signal, and you ask the question, is there anything left? Is there a residual that I can make sense of? And again, these are tests that are being done, pursued nowadays. And with in very few exceptions, when you can't compute signals beyond generativity, and I'll tell you why later on in the talk, this information is being used to further refine these tests. So it is complicated, but depending on what regime you're actually looking at, there might be some clean stages where you can say, well, maybe here I have the best chance of testing GR in a very strong way. So what's that state? Well, first is the observation. You just look at this and superpose is the result from numerical relativity, so for the full general relativity thing. And you say this is so simple looking on one hand. So it's just sinusoidals. They go up a little bit in amplitude, go up in frequency, and then it decays. Then maybe GR is doing quite a good job. Waveforms are very simple looking. Maybe there are some simple arguments we can use to efficiently encode this information, efficiently go after what potential deviations would be. And this is pretty much the name of the game. And it's awfully tempting to say, by looking at the waveforms, that the system is behaving so smoothly, so kind of uninteresting in some ways, not showing any craziness here, that the system is behaving essentially linear. This is in between big quotes. Because it's obviously not linear. It's not the fact that you can add two solutions and you'll get a third solution. But it's just this kind of bad terminology to say there aren't surprises here. I don't see anything crazy going on. It's a smooth sweep up in frequency. It's a smooth sweep up in velocity. At some point, a common horizon forms and the system decays. So we're going to get more into that. So let me just take a step back, put all of us in the same footing as to what things we're going to use for the test that we're going to carry forward. So generativity was this very complicated theory. People struggled with it for a very long time, even early on doubting about the reality of gravitational waves. Even Einstein himself, the paper he sent for publication was basically saying gravitational waves are not real. It was a referee, the one that corrected them, and the paper got changed on the proofs from the non-existence of gravitational waves to the existence of gravitational waves. So, but some golden oldies that Match is writing on are these observations. For instance, well, black holes are this one-way membrane in solutions of the theory, where at the classical level, information can only go in one direction, nothing can come out. And associated to that, we have this cosmic censorship conjecture that says every singularity that might be in nature is hidden by this horizon, and therefore we don't have to worry that classical physics is breaking down. We can do physics safely outside. Then we have some very basic black hole solutions. The one that we think is astrophysically relevant is known as a curved black hole that is described by 3 parameters: mass, angular momentum, and potentially charged, but astrophysically we believe they should be neutral, so only 2 parameters govern them. This is a solution that is extremely special, and we use it so much that sometimes it gets lost how special this solution is and how brave must one be to rely on it so strongly. The solution is found by assuming axis symmetry and stationarity. So 2 very, very, very special conditions. So, I usually do this example. If I assume stationarity, I can imagine a pen standing on its tip is a solution. But of course, no one expects to enter a room and finding a pen standing on its tip. For that, we need to find out where the solution is stable. This is something that later on was tackled, and I'll say more about that in a second. But associated to a curved black hole, we have some very key kind of concepts. One is that there is the so-called innermost tabular circular orbit for particles, for test particles. So just as in Newtonian mechanics, we know we can set up binary systems that have stable circular orbits and it will go on forever. In generativity, that's not the case. For test particles, we can do it up to a point. From some radius inwards, no circular orbits exist that are stable. So with just anything there within this innermost state of circular orbit, things will just fall in and have a merger. A similar concept exists for massless fields or massless particles, which is a so-called photosphere. And there is also something called the Anergosphere, which is this region very close to the black hole where things are dragged in such a way that you can tap energy from the black hole that is rotating and transfer that energy, if you want, to fields or to particles. And so things like superradiance or black hole jets are tied to this ability to extract energy from a rotating black hole. And the last kind of foundation that we can get from here is that there is the area law for black holes, that the area of a black hole never decreases. In every interaction, the area grows. Even when you take energy away, the area is growing. So here I'm going to the controversy. The controversy is related to the following claim. And the following claim is gravitational waves have already allowed for black hole spectroscopy. And I'll say a few more words about this in a bit. Essentially, you have measured enough properties of a black hole to put a very, very stringent test on, if you want, the multiple moments of a black hole, which in generativity say, if you measure one of them, you immediately know all of them. This is not true in other theories. So the claim is that with the current data, we have already seen more than one. Of course, the results so far observed are consistent with GR, so it's a freakingly strong test of the theory. And worse yet, or more important, or stronger yet if you want, you can do this in such a way that even you can push all the knowledge that you have, that you know in the linear regime, all the way up to the merger epoch. So already from the moment where two black holes become one, you can do a linearized approximation to describe the system. This is a really bold claim. And we'll go on through the evidence. So this is a claim by EC and FAR, but Carullo and collaborators and others are pushing back. This is with respect to the data. With respect to theory, you can also do that, and we're going to go through the analysis in a bit. These are claimed by Gisler and Tukolsky, and this is a very strong collaboration, and some authors here are from the same first line. So EC is a co-author here. But of course, there are others that are pushing back, and Ota describing her talk, their ideas on this. So let me review a little bit of the evidence, and then we're going to go back. So I'm actually playing like a role of a district attorney, and I'm pushing back on this claim. This is my bias, and I'll tell you why. So imagine you have a black hole. Remember I told you we had this curve solution, and we are using it as a foundation to describe a black hole accreting. The EHT collaboration published image of a black hole using intrinsically that the curve solution is stable. So how do we know that the curve solution is stable? Well, we know it for the following reason. You can take perturbations of a curve, and if those perturbations are massless, that's an important caveat, what you find is all those perturbations decay exponentially. And they decay with kind of an oscillation frequency and a decay frequency, and if you combine this, the decay rate and the oscillation, you obtain out of that the mass and spin of the black hole. And any mode that you can think of, say described by different L and M modes, they all give you the same information in general relativity. So what is this a little bit more in details? Well, you assume that your solution is described as the solution for the curved black hole plus a small perturbation. You put this into Einstein's equation at the linear level, so you assume a linear approximation is good. And then you ask, what is the behavior of solutions that have this shape, some exponential to some I omega t, and this omega could be is complex, so it has both a real and imaginary part. So a real part will describe these oscillations, and the imaginary part, if it has a right sign, will have the decay. If you find any evidence of the wrong side, you're going to have an exponential blow-up, and you don't find that. You always find an exponential decay for massless perturbations. So, of course, these modes, you can say, well, it could be labeled by L, the angular momentum number, an azimuthal number. When you plug in, you find more than one solution for a fixed set, or for a fixed value of L and M, and this N is overtones. So these are the further solutions you can have for fixed L and M. So this is some plot that shows like the real part in the left-hand side, and this is a Q, so it's the inverse of this omega. So it just basically says how quickly the system is decaying away to zero. And depending on what values of L and M you pick, they decay faster and faster. So the higher the L, the faster the signal is going to decay. So when you collide two black holes, you expect that the fundamental mode, the one that is the strongest in general, will be given by the L equal 2. And associated to that, you're going to have different frequencies. And of course, in the right-hand side, in the horizontal axis, what you have is the angular momentum. This is A, the parameter A. It's 0 for a non-rotating black hole. 1 is for a maximum rotating black hole.
So you just do is collide the black hole. You say that's a linear perturbation, collide the black hole?
No, okay. Great, but that's exactly where I'm trying to go after. So after the black hole merges, you first solve the problem in full. You take numerical relativity, say, and you see in full, and you see a waveform that looks like that. A few oscillations, it goes up and down. Then you say, well, can I rely? So I see that if I wait long enough, the system decays to zero. So there is a regime here that maybe a good description with respect to a curve solution exists. Not only that, you say, well, if a good solution with respect to a curved black hole, the curved black hole being a good approximation to the solution here should be good, it would be consistent if the mass and spin I measure here are the mass and spin I can predict I would form from the individual parameters of the system early on. And you keep seeing this consistency. And this goes to this ultimate thread conjecture, a conjecture by Israel and Penrose, that said, well, if you wait long enough, a collapse scenario will give rise to a Kerr black hole. And it seems that you don't have to wait that long before a Kerr black hole with some small perturbation is a good approximation. So, but thanks for that. Yeah, so here what you're saying, well, the outcome of the merger, that's an assumption that is supported by first the numerical simulations and then what you see in nature in gravitational waves. There is if you wait sufficiently long after the merger, a good description should be possible using this terminology. And then the question is how many of these I need? Maybe I need many of these modes to do a good description, and this is part of this controversy or what underlies this controversy. Let me just make one observation before I move on. So take the L2, the M2, I told you these are the fundamentals. These are the ones you believe will have the strongest content in general. And let's consider the slowest decay in overtone, the next slowest, and the next to next slowest. First, let's look at the frequencies, the real frequencies, the oscillatory frequencies. In whatever units of M, this is, let's say, the 0.53 is the fundamental one, 0.52 is the next one, and 0.5 is the next one. So these are three oscillatory modes that have almost the same frequency. So they are ringing at about the same frequency. But the decay rate is significantly different. So it's 0.08, 0.24, and 0.40. So this one dies much, much quicker than that one. This one dies off much, much quicker than that one. OK, let me review. I'll get back to this in a second. But let me review first that claim, the first claim. At the theoretical level, we can use linearized perturbation theory, this is the claim, to describe the behavior of this decay of the black hole almost all the way to the merger itself. So what did they do? You take a numerical simulation that has been specifically tailored to be extremely accurate. So it's the most, let's say, the most accurate waveform you can get. You get the waveform, say that waveform, and you say, I'm going to insist on trying to see if I can fit that waveform using simply the linear analysis. And then you ask, well, if I use only, and I'm going to insist also only of using L2, M2. I'm going to put 1 over the fundamental overtone, and as many as I need, and ask the question, can I get a better and better fit to the data obtained numerically at the theoretical level? So if you put the first overtone, that's the signal. So here what you're measuring is the signal that you have obtained analytically, well, numerically, with using general relativity and a numerical code, minus a signal that is just, let's say, first, just A0 e to the I, let's say, omega 0. By that I mean L2, M2, and N0. So I said, I want to fit with this. Can I do a good fit? And then you say, well, I have my true waveform. I do the inner product with my test waveform. Oops. And then I get a figure of merit out of here. I say, how good is this? So I can do 1 minus this one, let's say. If this were exactly equal to that one, I would get a 0. And that 0 will be the mismatch. And anything that is away from 0 would be the error I'm making in thinking that this is a true waveform when in reality it was that one. So that's for 0. Then you can say, well, let me put 0 and 1. That's that one. 0, 1, and 2, that's that one. And the more you actually put, they go all the way to 7, not only do you get a better match, but you also can push earlier and earlier and earlier to have a better fit, all the way to 0. And so that's the claim. The claim is you can go almost up to the point where these two objects got to merger. By that you mean the highest peak in the waveform. From there on, it seems that a good match is obtained by simply using a model that relies on just a linearized analysis. So you have sum from n equal 0 to 7 of an omega n. and just using the fundamental overtone. Of course, this is a merger of two equal mass black holes that are non-spinning. So that, let's put that on the side. That's evidence number one. Evidence number two is the experiment. You go to the data, you go to the loudest event, which was the first one, GW150914, and you do the same analysis, but with the data. You insist of just using this, and this is the H detected. And the claim is that the evidence favors having not just the zero mode, the zero overtone, but also favors having one and potentially having two. So the claim is that you do a better job feeding the data if you use more than one overtone. Not only that, there is a practical implication, because if you use just the zeroth mode, the zeroth overtone, you would predict that your signal or your parameters are consistent with this this ellipse here. But if you add one or two, you shrink it and you move it around this point, and this is the point you knew the answer should get, because from the earlier in-spiral regime, you could detect, you could draw what the masses should be, and from there, using a lot of theoretical analysis, relying on numerical simulations, you can predict what the final mass and final spin of the black hole. So the claim is if you only use the zeroth overtone, you don't get a better, a reasonably good fit. You can do a much better fit if you include the overtones. So it seems that the evidence here is uncontroversial. We should be very happy. You can do a much better match. You can get more than one overtone. And with that, you can even begin to write or be calling an agency to buy your ticket to Sweden. Because this would be amazing. It would be not only the detection of gravitational wave, but the spectroscopy. Yes?
Sorry, I don't understand what the claim is.
Okay, the claim is here that, let me put it this way. Each one of these omegas are independent. So each omega, it depends on the mass and the spin of the black hole. Measuring only one of them, because you actually have two pieces of information, the real and imaginary part, you can get the mass and the spin out of this. And if you measure two that are independent, 1 and 2, you can have a very, very strict constraint on what, if you want, out of this you get the mass and spin, you predict which one this should be, and that's what you get it. So the claim is that in the data, if you analyze it, you get not only the fundamental overtone, but you get at least the first one that comes after one.
The omega is complex, it's two parameters.
Yeah, that's what I said. So this one, you can get two equations out of this. You get the mass and spin. With this one, you can predict which this one should be, and that's what you're getting. So that's a claim, that the data already favors a model with that. But that claim, okay, the moment you buy this, you're beginning to buy further other things, which is what I'm trying to push back on. So the claim, the overtones of a black hole have already been measured, at least two modes, the fundamental and the first overtone. So this gives you a black hole spectroscopy, two independent measurements, which has very strong evidence for GR, and of course, have practical consequences of the source identification. It gives you a better sense of what the parameters of the source will be. The results are obtained as in GR. People call this the no-hair theorem test. I don't like the terminology because no-hair is a statement for stationary black holes. These are not stationary black holes. This is a much stronger test. So I really dislike people using no-hair theorem tests when they are doing much more than that, out of which one consequence is a no-hair. What they're doing is testing the ultimate state conjecture, that this system very quickly relaxes to a black hole given by Kerr. But not only that, already from the merger itself, the system is describable in linear terms of the Kerr solution. If that's true, well, that gives you very strong confidence in even the template construction that you need to do to efficiently encode information to go after signals. But if I keep going down rabbit hole, I don't see any way I can get out of the following claim. I just collided two objects that are afforded one. So I take one, I hit it with another one, and the system is behaving linearly? So what the heck? So this means that black holes do more than just high singularity. They also find a way to hide nonlinearities. And that is like a tall order for me. It's going to take me a long time to believe that. So I'm going to go around and say, well, can I have arguments that are strong to claim that we should be careful when we do this kind of analysis? Okay, so first, this is where I'm going to start trying to push back a little bit. So let me first, recall where we come from and some of the potential problems associated with that. So any time we use any perturbation to study any system, we have some dangers. And since we've been using perturbation theory for such a long time, sometimes we forget about them. And this is perhaps the reason why I went into numerics, not on perturbations, because I always find that kind of iffy. So depending on the type of perturbative scheme I choose, I might hide some potential issues that for that I need to work out higher orders before I can understand it. And different strategies might give me different answers, and only through suitable resummations I can put everything in the same context. So let me give you a very specific example. Take Navier-Stokes, for simplicity, in the incompressible case, divergence-free. So the equations will be given essentially by this structure. The time derivative of velocity, then there's an addition of the nonlinear part, v dv, and the dissipation, some eta over rho, whatever, Laplacian of the velocity. So now you can choose your perturbative scheme. I'll tell you one, smallness of the velocity. So if I use smallness of the velocity, this term I keep, this term I throw away because it goes like velocity squared, and this term I keep. So all of a sudden, my equation tells me that velocity will decay exponentially with a rate given by n. So now what I've gotten is a solution that tells me all fluid description is laminar. I just have decay. My perturbation is decay. Let me choose a different perturbation scheme, which is a perturbation scheme based on the gradients. I said derivatives are subleading to higher derivatives of the same field. So here I have a first order derivative. Here I have a first order derivative. Here I have a second order derivative. I throw this away, and I obtain the solution to this equation. When I do that, what I find is all modes are turbulent. So I recovered a turbulent regime, but I lost the laminar regime, and vice versa if I did the R1. Of course, we know better that if you compute the relationship between this and that and which one wins, we arrive at the famous Reynolds number in fluid dynamics, which tell us if you're below this one of the perturbation scheme is a suitable one. If you're above, the R1 is a suitable one. So we have to be very careful when we stop a linear and we don't know anything about the higher order. So in no particular order, I'm going to give you 3 arguments for what I think we should push back on people trying to buy a ticket to Sweden so quickly. So, and for that, I'm going to go here. I'm going to remember this quote by Ulam. And this is saying, well, using the term like nonlinear science, like referring to the bulk of zoology as the study of non-elephant animals. So what I claim is, well, linear perturbation is us studying elephants. There is a whole zoo of animals in the zoo or in nature that we have to be very careful before we dismiss them or not remember that they are there. So first, I need to make sure that I remember something. We sometimes, again, forget that we use 2 subtly different terms, sometimes interchangeable. Linear stability and stability are not necessarily the same. So linear stability means the solution to your full problem in the small regime, in some code, is the same as the solution to the linear problem in that small regime. That's not necessarily the case, always. And stability is just that the system decays and nothing weird happens. So the example is take your coffee and stir it. There is nothing that goes stable unless you're crazily and then just everything spills out. You just stir it a little bit. This problem there is definitely stable, but it's not linearly stable. You perturb with a given mode, and other modes will be created due to nonlinear interactions in the fluid. Of course, they might be very subtle, might be very small, might not be very obvious, but if you put your Fourier glasses, you will see these other modes being created. So what evidence do we have? And some of this has been there for a long time, that nonlinearities are present, even in the merger of two black holes, from very, very early on. So one example was this. This is a work that was done back more than 20 years ago in the so-called closed limit approximation. Back then, we didn't have codes to collide binary black holes orbiting. The best we could do is just head-on. So people were doing head-on, and at some point, the same strategy was pursued. They said, well, at some point, these objects are coming so close that it should be able to describe, with perturbations over Schwarzschild. And perturbations were carried out to first and second order, so they could actually ask the question, if the merger takes place, how do I get a better fit if I use the first order or the first and the second order? And you can barely see it, but the true signal is a solid line. If you just use the first order, this is a dashed line. If you use the first and second, you do a better job. So it's already hinting that further stuff is there, and the linear perturbation, the linear analysis was not able to capture everything. Another thing that we did also a long time ago was to ask the question, I have a black hole, I'm going to imping it with some packet of gravitational waves, and I'm going to get the scatter signal. And if the problem were linear, the signal that gets scattered, if you divide it by the amplitude of what you throw in first, should always give you the same answer. And here these lines show that for a large value, large set of very small values, indeed everything lines up on top of each other. But as you increase it, you got further and further structure that the linearized analysis would not have captured. So that's evidence number one. It was there. Evidence number two is what I said before. If you really want to rely on or understand or see how much you can rely on your first order theory or approximation, you should work out what the second order perturbation would be doing and then compare. So very recently, people have undertaken that. It's complicated for Kerr, but there is a series of new works where you basically say, well, I already had solved, let's say, the linear problem, and the second order problem will have this solution act as a source for the second order. And you can, once you solve all that, you can show that for a perturbation that has, say, the H1 has this size, it induces a second order perturbation that, albeit small, it's there. So in the virtue of time, I'm going to be just basically going to the punchline in most cases, but tell you what the basic solution is. So some years ago, also in a very different context, this is related to ADS-CFT applications, we were asking about the quenching of a system, of a Hamiltonian, so where you had some object, the dual picture of the quenching problem was a black hole where you're going to hit it. And you're going to, the experiment was such that you could hit it in any way you want, ever so slowly, or just punching it with the same amount of energy, but with a very, very short time picture. So what you saw there is you had a black hole, you send a pulse. If this pulse was extremely long in duration, what you found is that, okay, you're in the adiabatic regime, and the space-time responds in a very much the same way. So if I put an L2 mode, I got an L2 mode coming back. And that was universal. At the other end, where you did it extremely fast, there was another universal regime, which was highly nonlinear. But when you ask, in the collision of black holes, what type of punching are you in? Are you in the very slow regime or in the very fast regime? And the answer is you're in neither place. You're in the middle. This time scale of the perturbation, if you want, is order m. The time scale of the decay of your black hole is to a Kerr black hole is order m. So you need to understand this in some better fashion. But deep inside, what they are doing when you think that after the black hole merge, let me go back here for simplicity. Imagine, let's go here. When you're here, if you're actually going to believe that from this peak of the waveform onwards, you can do a very clean decomposition using a linear analysis, what you have to remember is that each of these modes are modes of the black hole that has mass m and spin a. But as the process goes on, some of the energy falls into the black hole. We know by the area law that the black hole will change its mass ever so slightly, will change its spin ever so slightly. So now a pure mode for a black hole of mass m and spin a is no longer a pure mode for a black hole of mass m prime and a prime. So you would have a collection of new modes, which already says this is just too naive, because that frequency there that knows about mass and spin is changing because the mass and spins are changing. And so we have this result very recently that basically point out. And the last example I'm going to give goes back to the following as well. So a black hole that has some gravitational waves around. So I just formed this black hole. There is still gravitational waves around. These black holes are propagating. These gravitational waves are propagating. But as they propagate, they introduce some time dependence of the system. It sources slow, small changes on the space-time themselves. And the equation that you should be considering is not that G, the metric is the metric of curve plus some perturbation. In reality, what you want to think is that the metric is some time-dependent metric, slowly varying because of the presence of that guy. Then you can ask the question, how does a perturbation behave if my space-time is curve plus something that slowly is varying with respect to the space and time? And what you find is there is an instability, a parametric instability for some modes that says this energy in this mode will couple with whatever other very tiny, however small mode is, and will preferentially send its energy, or some of its energy, into those modes. So that calculation we did some years ago. It doesn't matter the details, but parametric instability is something that is taught in classical mechanics. Usually it works out when some conditions are met, and the conditions are here. It doesn't matter, this is a mouthful, but basically you're trying to make this thing the largest possible, which is the size of the perturbation divided by the azimuthal number and the decay of that mode itself. Okay, what does that mean? I'm going to do this exercise. Take that amplitude, and let's think in fluid terms. In fluid terms, the amplitude of the perturbation is my velocity. The 1 over the azimuthal number in fluid terms is like a wavelength. And the decay is given by the density over the viscosity parameter. So just by putting the natural analogs for fluid coming from gravitational waves, or from gravitational concepts, what you arrive is this. And this is nothing but the Reynolds number in fluid dynamics. So you encounter that the equations that determine general relativity, hidden in it, intrinsically, have something that very much like are with fluid, and this is something that is not the first time has been discussed, but it also points strongly to nonlinearities being present regardless, and it will do something like this. It's going to be channeling energy from one mode into another preferentially. So let me just summarize here. So there are compelling indications, from my point of view, that general relativity in the area ring down is not linearly stable. I have hopefully identified several mechanisms for you that channel nonlinearities actually do some interesting things. Further modes be created, modes varying in time, and not be cleanly represented in these ways. I argue, even though I didn't go into too much detail, that the relevant time scales are such that are commensurate with the source time. So source time and the relevant time scale for the decay are the same. If this black hole were decaying at a much faster rate than, say, this waveform here, then you could perhaps say, well, I already have my curve solution, and I can imagine the rest is perturbation. But the lifetime of this and the lifetime of the decay of this perturbed black hole are about the same. So we are in that intermediate regime where the interaction is non-trivial. So, but I told you at the very beginning, we have the evidence. There were these two claims. So what am I saying? Am I pushing back? But what am I pushing against? I'm not pushing against the fit. I have absolutely no problem that you can do a better fit with overtones than with just the fundamental ones. But I'm very strongly against the overinterpretation, which is to say that the fact that I can do this better fit implies that the system is behaving linearly, implies that the spin and mass that I'm measuring are the mass and spin of the black hole. I think it's just an artifact of the fact that of what I pointed before. that the overtones all have more or less the same oscillatory frequency. They have, however, a very much faster decay. And so whatever off I am in amplitude, I can add these overtones to just shave off the little bit that I'm missing, very much like what was already seen a long time ago here. This is the first and second order, and the other one was the first order. There is not significant difference in phase. There is just difference in amplitude. So what these overtones are giving me, by essentially for free, is an object that oscillates in the same frequency, but I can put here that will have no consequence there because it dies much faster. So that's what I think is going on. And with that, I will stop. Thank you.
Questions?
Hi. Thanks for the nice talk. So I have two questions. The first question is about observations. What would you need? What kind of an observation would you need to conclusively prove that this is what's going on? And
OK, so you want me to answer that? To conclusively, so I think that of course, I'm completely biased here, but I think I have conclusively proved that the system cannot be behaving linearly from the get-go. Already, you can do the second order calculation, and it's introducing some contribution. You can observe that your black hole there is changing its mass by, say, 1%. That will impact the description of modes. A pure mode will no longer be a pure mode. And here, this assumption relies on a pure mode stays a pure mode. You're just adding more overtones. So I think from I would flip it around. I think any extraordinary claim should be backed by extraordinary evidence. And I think there is no extraordinary evidence. And in front of this, I think there isn't a case. However, as I said, I have absolutely no problem whatsoever in saying this is a better fit. And it's convenient, and I think it's an artifact of the way these overtones are working.
And my second question is about a paper by Sean McWilliams from a few years back, which you also, I think, cited. So they claim to construct the waveform from the ring down backwards. According to this, it should be impossible. Would you agree with that, or no?
No. OK, so just to give a little bit of context, so I'm going to stop here. Yeah. No, let me put here. OK, so let me start first with this one. So I mentioned very quickly the photosphere. So the photosphere is almost the same as the innermost circular orbit, but for massless field, which of course include photons, but also gravitational waves, or gravitons. There is a way to connect the location or the natural frequency associated to that with the quasi-normal modes. So what does Sean do? So Sean is saying from after the merger, I can fit that behavior using that frequency. Of course, what he's doing explicitly is he says that in the paper, he's getting, in a sense, the quasi-normal modes for free, built in. Then he uses an interpolating function between the crossing, say, of the innermost circular orbit or the photosphere to the peak of the waveform to merge with the earlier behavior. But what I'm saying is this doesn't preclude Sean. So Sean could choose to use early on a collection of overtones, and the fit will very likely be better. So I have no problem, as I said. This result, I mean, this is really good job. It's a very careful job that is saying if you keep adding these things, you're doing a better match. And that I have no issue with. I do have problems if someone wants to use that and say this implies the system is behaving linearly.
So thanks for the talk. You told us that the frequencies are kind of similar, but the
decay
damping
rate
time is different. But with better precision in the black hole spectroscopy, we could distinguish between just, I mean, what you told is happening and what people are telling us.
Oh, yeah, you're absolutely right. So, in fact, what you do, I mean, so nowadays, going back to here, so there is another plot. Yeah, so let me say two things. There's another plot in this work that basically says, so if everything behaves linear from here onwards, well, let me use the first stupid example first. When I take a snapshot, when I take a selfie, which I don't do, but if I take a selfie, my face is represented by a whole bunch of Fourier modes. Of course, I think I'm not a collection of Fourier modes. But then when I move it a little bit, there would be a time dependence of those coefficients. So if the system were behaving linearly and I do something at t equal 10, my choice of parameters will uniquely fix everything afterwards. So if I match at 10 and then I choose to match at 40, I should extract exactly the same coefficients if there is signal left. The problem is that we're also fighting the fact that the signal is dying, so the SNR decreases. And there is some evidence that these coefficients are fluctuating. So already that's hinting at what you're saying. Eventually, if I have whatever, LIGO of 25th generation or 25th generation detector, my SNR will be so low that I will be able to tell, and that will pick it up. Yeah, so it's funny that, so we're having this discussion now because the other detectors are not available yet, but eventually we're going to go there.
Yes.
But yeah, thank you.
Okay. Going once, going twice.
Ricardo?
Yes.
So thanks for the talk. I wanted to ask if you could describe a little bit more about how to treat nonlinearities in the early ring-down regime if you use like hydrodynamic techniques to treat turbulence in fluids that are not in the relativistic region.
Beautiful question. I hope I knew the answer to that. So short of doing the simulation and getting them, there is something else, however, which is hinted a little bit on this work, but also on the work of turbines. So there is usually the eddy turnover times. So there is more than one time. And so there is something that I know people have been relatively successful with in some regimes, is to say, you go back to this equation, you still assume that these things are put, but now you promote these guys, the coefficient, to be time dependent. So this is going back to the previous question. But they are time dependent in a different time. It's a second time. So it's like, 2-time scale expansion. So then you put this back into the equations, and you obtain an equations for the coefficient. And then what you find out is that there is, of course, a nonlinear interaction is manifested now in the equation of motion for the coefficients themselves. And you can reveal the second time scale there, and what you're then able to capture is how energy is transferred from one mode into the other one in the right regimes. And this, what we did here is essentially that, but in a much simpler system. Where we can do that in general, that would be a complicated thing. Now, what Lars Berna and Pablo Bosch are exploring with is to just pick the fundamental mode, have just the A0 here, so go back to that one, but promote these guys to slowly varying coefficients. And they do that because they say, well, but we know the mass and spin will change. So can we have a fiducial or sufficiently simple but supported time dependence for this guy that then we can exploit for the fitting? And it seems to be, I've only seen preliminary work, that they can do as good a job as this one with perhaps just a couple fewer parameters. But what they are doing is just now capturing that slow variation that is, is happening on the physical grounds, and then this gives you a couple more parameters that then you can fit. But I wish I knew the answer to your question.
Okay.
Nathan?
you answered it, but maybe I want to be more explicit. So if I understand correctly, you're saying that gravity waves today cannot capture linear deformations of black holes, right? That you, once you get to the linear part, you lose the signal.
Okay. Yes, great question. Let me try and answer in a slightly different way. So this is not the waveform, but just because it shows it clearly. So suppose the merger happens somewhere time there. So it decays very fast. Given today's sensitivity, you can only capture, in a way that no one else will dispute, for some sources, the fundamental mode. I think most sources, they haven't even captured the fundamental mode. But the very first one, and there are a couple more that has an SNR of 20 or 30 or thereabouts, the fundamental mode, the L2, M2 mode that happens afterwards, has been captured. The next one is just decay so much faster that you don't capture. And that's the beauty of this L2 mode, the one, this one overtones. They're not decaying as fast. So you have let me just go to Bertie's thing. You have two options. You can say, I'm going to capture different L's. I mean, first, the system, unfortunately, or fortunately, is being driven by a very specific thing. So it's an M2 mode, and these two obviously are going away. Also, the systematic or the observational bias that LIGO has, or the gravitational wave detectors have, is they will detect the strongest sources. The strongest sources are given by the equal mass binary case. And so you're driving with the M2, and the larger the L is, the faster it's decaying. So it gets more difficult. And so for these modes, especially that one, this one is not decaying as fast as the L equal. Well, first, the L equal 3 mode, because you're in the equal mass case, is not strongly sourced, while the L2 mode is sourced. This is why the very interesting choice was made by these groups, to go after the overtones as opposed to all the L's. The traditional black hole spectroscopy that people had been discussing was to go after the L's. And for that, well, the first claim was that you needed to wait for LISA to fly to have sufficient SNR. But the potentially saving grace is that if you're thinking that the theory is GR has no intrinsic scale. So in principle, you could stack many, many signals. So we had a work some years ago where you say, well, maybe you don't have to wait for LISA or third generation detectors. You just have to suitably stack them if you have several hundreds events, but we're on the way there. So maybe we don't have to wait for LISA, but for seeing clearly in a single signal, we either need a binary black hole merger at the other end of the corner, or we need much better detectors.
Okay, last call for questions. Then before we move to coffee, let's thank Luis again.
The ones who did the study with the varying omega?
With what?
With the varying omega, with the time dependency in omega?
Laura Sperler.
Ah, okay.
And Pablo Bosch.
Okay. They're 3 minutes, no, where are they?
No, Laura now, she's at AI. And Pablo is